piece of this, I'd like to talk about competing risks. So we had talked about those last time, but there's a point I didn't have a chance to make last time, which bears mentioning. So we have a competing risk situation where we have a delay that otherwise might be a first order delay, except we have a second flow out of it, and it goes either out with one or out with the other. Either you develop end-stage renal disease or you die before end-stage renal disease, one or the other. Mm-hmm. Now, when you have a situation like this, unexpected things can occur. So we have a situation where it drains, and it drains down in a familiar fashion. What does this look like? First order delay. It's just draining down. Suppose we add one rate constant of 0.03 over here. Notice we have a mean time here. The rate constant is just what compared with the mean time? It's just reciprocal of the mean time, 1 over it. So if we have a mean time of 10 years to develop end-stage renal disease, the chance per year of going, if we just represent it using a first order delay, the mean time is simply 0.1 per year. Each year, there's a 0.1 chance, or on a per unit time basis, it's 0.1 per year. It's actually a continuous process over the course of the year. If this were 0.1 and this annual risk of mortality were 0.2, how would this drain? Give you a hint. Well, okay, that's true. What's the formula for this guy? If this is 0.1, if the rate constant of 0.1, chance of 0.1 per unit time, what's the formula for this guy? Stock times that, right? Formula for this guy is stock times the appropriate rate constant, right? As far as the stock is concerned, it's being drained with a rate constant out of it of the sum of those two. As far as the stock is drained, there's a 0.2 chance going this way, 0.1 chance per unit time of going that way. So there's a 0.3 unit per unit chance of going one way or the other. So it's being drained quickly according to sort of a rate constant that's the sum of these two rate constants, right? And that's, that leads to this familiar drain. So you have something going out like this. This is the rate constant for one, alpha. This is the rate constant for the other, beta. Just the sum out. After all, suppose those, that stock doesn't care where those flows go to. Those two flows could just both be going out into clouds. In fact, it's divided across 2 versus 1, and the stock doesn't care. It can drain just as quickly. So these could be two parallel ones going out. It's the rate constant associated with the rate at which it drains, the chance per unit time of leaving is the sum of the rate constant for this one and the rate constant 0.2 plus 0.1. Does that make sense to people? Okay. Now, the interesting thing is not so much that. So it gets drained faster. Fair enough. The interesting thing is, how does what goes on here, say, on this flow affect what goes on that flow, and vice versa? This is where the competing risk things come in. And there's some effects that are just not completely obvious for this. So, suppose you tell me, a Gedanken experiment. Suppose we were to double the risk of diabetes, right? Yeah, diabetic mortality rate. Gosh, that's let's flip the Gedanken experiment around. Suppose we were to halve diabetic mortality rate. So we were to reduce, wonderful medical breakthroughs, we were to reduce the rate at which people develop diabetes. Suppose we could. We could even imagine doing this with several stages, affecting one group more than others, but suppose we could just reduce for diabetics the chance of dying per year basis by factor of 2. How would that affect, first of all, would that affect this population with the ESRD? Okay. Give me some intuition why it would affect it at all. I mean, after all, aren't we just affecting mortality? What does it have to do with the ESRD? Okay. Good. So they have, and I think Kurt was getting at it, they're staying alive longer on average. So they have a longer period of time over which they might develop ESRD, longer period of time over which they're subject to ESRD. This has nothing to do with death and ESRD in general. In any case where you have two competing things, this could be, you buy this product or that product or whatever. I mean, it doesn't matter. The point is because this flow is lower, this vertical flow, this other flow, the stock stays higher, and therefore they have a greater chance of actually going down that flow. To put it another way, let's flip it around. Suppose diabetic mortality, this lower flow here, suppose that were extraordinarily high. Do you expect fewer or more people to get diabetic end-stage renal disease? Fewer. Okay, so that's an intuition. Now let me ask you this. So fewer people will get it because more will be done, right? Okay, fair enough. So we said this is the mean time to develop diabetic end-stage renal disease, and we could talk about the rate constant. It's just if this is mean time to develop of 10 years, what's the rate constant? What's the chance per year of developing it? 1/10. Okay. So let me ask this. Is the time with which someone develops end-stage renal disease always truly this mean time to develop end-stage renal disease, independent of this other flow?
Is your question, does that always mean the mean time?
Yes. Okay. So I'll flip it around. If we had a higher risk of dying per unit time or a lower risk of dying per unit time, would that affect the time, the average time with which someone develops end-stage renal disease? Okay, so some conflicting feelings on this? Suppose this rate of death were extremely high. Who is it that would be getting end-stage renal disease? Would people have to get it sooner? Okay, suppose this chance of death was 0. Would people have a longer sort of period of time over which they could develop end-stage renal disease? If this risk of death were 0, do you think it would affect the timing of this?
In the diabetic population, you'll have some people get it in 10 years. Nobody's dying.
Okay.
Those people that would have gotten it in 10 years, if they're dying now, they're going to die before they get ESRD, which means they won't show up on the ESRD, which means that even though you've said the average for a healthy population might be 10 years, if you're killing off some of those people, they can't get an ESRD anymore. So you kind of, the only people that get ESRD are the ones that get it before they die. So you're skewing the mean time so small.
Yeah. So it actually turns out that the answer, ladies and gentlemen, is yes, it does affect actually the timing here. And if the competing risk is very, very high, it's going to skew things, for example, towards the early side. The only people who can get down here are ones who are going to do it pretty quickly. it's going to really censor a lot of people who would have done it later because they're dying first. And so Kurt expressed it very well. Now this is counterintuitive. I mean, after all, aren't we saying mean time to develop? Well, it turns out there's some subtleties here having to do with unconditional probabilities and conditional probabilities and so on. But let's take the effect of doubling the diabetic mortality rate. The effect of doubling that diabetic mortality rate would be to raise from the blue to the red the deaths, right? Here we have the deaths occurring. We double the diabetic mortality rate. People are going to be dying more quickly in larger numbers, and so you have greater rate of death, people per unit time, people per year, people per day. The diabetic population will be lower or higher as a result? Lower. Be lower as a result. And therefore, there will, this is the first question I asked, indeed be fewer people who ultimately develop end-stage renal disease. Because there are fewer people who are candidates per unit of time for becoming a smaller population susceptible to end-stage renal disease because so many extras have died. There will be fewer people getting end-stage renal disease. So you do get this coupling phenomenon there. And so in terms of mean times, if we double it, the fact is we do get a different mean time. So this is a graph of the flow here, from here to here. Okay, this is a graph of the flow. The number of people per unit of time getting it. We could talk about the mean associated, the mean time of one of these transitions. We could take these as curves. We can normalize them and say, okay, some of them. One are the means of these different associated with these different curves. Turns out that the means are different. Which curve has a lower mean than the other? Which curve has a lower average time of transition? Time of transition is here on the right. Well, it turns out this red curve is skewed more to the left. You notice it's very much below the blue curve out here. It's equal to the blue curve here, so there's more people getting it early compared to later for the red curve. So people are developing end-stage renal disease sooner as a result of this. So you have a higher death rate. The diabetic population will rapidly decrease transitions. The ESRD will be skewed towards earlier transitions. That's the only time you're going to have a chance of developing end-stage renal disease rather than dying before end-stage renal disease. You have a lower death rate. The diabetic population will decrease less rapidly. Many will make the later transition to ESRD, and there'll be a later mean time to transition. We can look at this, I emphasized before, that is from the point of view of the stock that's being drained, stock of diabetics here. As far as it's concerned, it's just being drained by these things with these two rate constants. You sum up the rate constants, that's how fast it's being drained. The mean time to leave is actually given by this formula here. And you'll notice so yeah, this is the mean time to leave here, and if we have beta be 0, there's no competing risks. What's the mean time to leave? Alpha here is the rate constant. It's 1 over alpha, which is the mean time. We have a rate constant, it's 1 over the mean. Mean is 1 over alpha. If beta, that's if beta is 0. In general, the larger the value of beta, the smaller this expected time. If beta is really, really high, if we have extremely high risks associated with this other transition, it's going to skew our mean time to transition here in this predictable way. So you have to be a little bit conscious of the fact that there is this effect going on. Now, you may think of this effect as just an odd, a strange effect. First of all, if you're going to estimate data for the mean time, this may play a role. The second reason this is important is because people don't realize this effect. And sometimes you'll hear discussions of disparities between two groups and how long it takes to develop a condition, say end-stage renal disease. And they're ignoring the mortality. They're not paying attention to the difference in mortality. And they're saying, oh, there's this disparity between them. And if you want to understand the cause for that disparity in the mean time to develop this condition, that needn't lie only with differences with respect to susceptibility to that condition. It could lie with respect to competing risks, like mortality. That, in other words, from a systems thinking standpoint, ladies and gentlemen, what goes on here affects what's going on here. And so focusing only on this, seeing differences in mean time here and saying, oh, it has something to do only with this, is missing the point it's affected by this as well. And that's potentially important if you're looking for causes. You're looking for explanations as to why. Okay, so I know that was a little bit technical, but the big point here is that these mean times, you got to understand when you have empirical data that empirical data is a different thing from this mean time because it is affected by these other parts of the system, and we do have this phenomena where one competing risk can affect the statistics on the other, and we want to think about that a bit. Okay, so what I've just done is tried to provide a discussion of